Alright, so we have gone pretty deep into the Serre spectral sequence and some computations, and we're going to go deeper, but I thought it might be a good time to take a breather and change tack a little bit. So I want to talk about spectral sequences for double complexes, and in this video I'll just introduce double complexes, and we'll get to the spectral sequences in the next video. Some good references for all of this material are Vakil's Spectral Sequences, Friend or Foe. Hopefully I've convinced you by now they're friend, but still a good article. Watch out though, there are lots of typos here, and that threw me off a lot when I was first learning. Another good resource is Weibull. There are some typos there too, but less in this particular part, and there's errata online, so that's good. And McCleary also does a nice job of all of this stuff. So let's define a double complex. And I imagine you've actually seen this before, but it's good to be really precise. This is also sometimes called a bicomplex, though I'll just say double complex. And really all it is a bigraded R module. So we're working over some commutative ring R. And sometimes I'll just write C, or I might want to remember that it's bigraded and write C star star, or you'll see that it's a collection of things that look like CPQ for all P and Q together with some differentials. And one of our differentials, I'll denote DH for horizontal. This is going to go from CPQ to CP minus 1Q. Notice that's going down in degree, so I am going to do all of this homologically graded. You could do it all co-homologically graded as well, and you'll see that in some of the sources. So I've got horizontal differentials, and I've also got vertical differentials, so I'll denote those dV. And at the PQ spot, that goes from CPQ to CPQ minus 1. Okay, so that second grading is denoting my vertical. And then I just want to make sure that these are differentials, so dH after dH should be 0, and so should dV, dV after dV. And then also I want dV dH plus dH after dV to be 0. So all of those should be 0. And really I'm just saying that each row, which looks like C star Q, is a chain complex, and also each column. So these are each chain complexes. And then I also want this last condition, that dV dH plus dH dV is 0, is just saying that all the squares anti-commute. So this isn't a commutative diagram. We set it up to be anti-commutative. That's really a choice of convention. Anti-commute makes the grammar work here. Okay. Well, anti-commutative would have worked just as fine. Okay. Anyway, my point is this is a choice of convention. Some people do it a different way and then define their total differential slightly differently, but we'll stick with this version. So what does this look like? I've got some big diagram. Maybe I have CPQ here, and that fits inside a chain complex along the rows. Yes, okay. I'm getting confused looking back and forth between my notes and the page. Okay, so sorry, bear with me. Maybe here's P minus 1, Q minus 1, P, Q minus 1, CP plus 1, Q minus 1. Okay, so that's also a chain complex. These, of course, continue on potentially. Let's get just a little bit more into this picture. So CPQ plus 1, CP plus 1, Q plus 1, and here's CP minus 1, Q plus 1, and there are also vertical chain complexes, so each of these columns forms a chain complex. Okay, and then I'm calling these horizontal differentials DH. As usual, maybe I should really call it DHPQ or something, but I'm being kind of lazy. And then I've got DH here, and so on. I won't label all of these, but here I've got DV, the vertical differentials. And each of these squares anti-commutes, so I'll try to denote that with this little minus sign. Okay, so I said that we're working with a bi-graded R module, but maybe let me just point out or say as a remark that you can work more generally. Certainly Weibull does, so you can work in any abelian category. And in any abelian category, you can define what we just defined. That's perfectly fine. But for what we want to do next, you would want your category to be complete and co-complete. And you'll see why. Well, that's because I want to define the total complex. And maybe I'll put the in quotes because I really want to define two at once. Though people tend to just say the total complex and be kind of sloppy. So there's one that looks like tote products of C, and there's another one that looks like tote direct sum of C. Okay, and so you just want to have nice products and co-products. That's why we want complete and co-complete. And really all we want to do is collect up along the diagonals. So we want it, whoa, supposed to be writing. I have no idea what just happened. That was so strange. Okay, sorry. So we want to have collect up our diagonals, and we collect these up either with direct products or direct sums. Okay, so to define this total complex, if we're in the product version, then in the nth degree, we just have the product over all of things whose total degree is n, right? And we've used this term total degree before, so this should be fairly familiar. Alternatively, we could do this with the direct sum. You probably didn't even need me to write that at that point. I think it's clear. Okay, in both cases, we can define a differential by taking dH plus dV. So that's dH is our horizontal differential here, and whoops, and then dV is our vertical differential in that double complex or bi-complex. And I sort of spelled this out by circling, but let me say this is just collect up the diagonals. And then make that new thing into a chain complex by defining this differential. So, okay, maybe let me say a good exercise, just to make sure that you're following all the indices, is that when you do this, you take D to be dH plus dV, that you do get that D squares to be 0, so that we formed a complex. And then we have these two versions, but if C is bounded, which I suppose could mean a few things, but what I mean here is so that CPQ is 0 for all but finitely many PQ with total degree n. So let's write that PQ with P plus Q equal n. Okay, so for example, if you had something that was just concentrated in the first quadrant, then you look back at these diagonals and you see, oh yeah, you're only going to be taking the direct sum or product of finitely many terms. And so in that case, they coincide. And this is part of why people just say the total complex, because tote prod and tote direct sum, they end up being the same, and this is often what people mean when they just write tote C. So this is the total complex, and most of the time we want to work in a situation where we are bounded. In fact, most of the examples that I'm familiar with are in the first quadrant, which is kind of where we've been working in general anyway. But we can generalize more, and when we come back and talk about convergence, we'll address that a little bit. Maybe just, if you haven't thought about total complexes before, a good exercise is that if C is a bounded complex, I should say double complex, and you know that C is nice, say it has exact rows, though there's nothing special about the rows here. So if you had exact columns, you'd get the same result, and what's that result? That you look at the total complex and it's also exact. So no homology. Okay, so next we want to take these double complexes and use them to get a spectral sequence.